Okay, well, good afternoon, morning, whatever it is for you. 11.3 bond polarity and dipole moments. This is for chemistry. And this is a very easy lesson, very short, a few problems out of the book, and we'll be done with it. We had talked last time about electronegativity, and electronegativity is defined as the attraction an atom has for shared electrons. And we mentioned that we can calculate the electronegativity difference, and if that's from 0 to, or it's less than 0.4, we have what is called covalent. I will often say nonpolar covalent if we're between 0.4 and 1.7. That's polar covalent. And if we are greater than greater than or equal to 1.7, this is called ionic. What we want to do today is look at the polarity of molecules. Polarity comes from the same word as pole. It means opposite ends. So let me start this way. Let's say that we have HCl. H has a charge, electronegativity of 2.1, chlorine is 3.5. This is a 1.4, which actually puts it pretty far over. It's a very polar molecule. It has two opposite ends. Why does it have two opposite ends? Well, because what happens is this will be sharing an electron. Actually, it'll be sharing two, but for right now, let's say it's sharing an electron. Chlorine is a bully. Chlorine wants that electron. So every once in a while, that electron spends time around the hydrogen. It is the sharing of the electron that's holding this together. And that molecule then is, the electron tends to be over here more often than not. Can't see that real well, sorry about that. The electron tends to be over here more often than not. Let's say that we had chlorine to chlorine. Well, chlorine has an electronegativity of 3.5, but so does the other chlorine, and the total difference then is 0. This would be our electronegativity difference. That means perfectly equal sharing. So what we would think of is that our electron spends as much time around one as the other. Okay? By the way, this is true regardless of whether it is a single bond. If I had water, H2O, by the way, water actually looks like this, and what's going to happen is they're going to be sharing an electron, but what will take place is that electron will spend most of its time around the oxygen, as will this electron. Every once in a while it'll be up here, every once in a while this one will be up here, but we will end up with a shape that looks something like this. This one then, if we looked at this molecule, this end of the molecule tends to be negative. That's because the electron is here most often, and this end of the molecule tends to be positive. Here, there's no opposite ends. Here we have a positive end to the molecule, and we have a negative end to the molecule. In most simple form, the positive end is the end with the least, smallest electronegativity. The negative end has the largest electronegativity. The electronegativities are the same. We'd say there's no opposite ends. Let's say we had something like sodium chloride. Sodium chloride has a positive, sodium is, I don't know if I have it here, but it's real small. It's like I do have it, 0.9, and chlorine is 3.5, so there's an electronegativity difference of 2.6. That means the electron actually gets transferred, and basically chlorine gets this all the time. And this then is a negative and a positive. We call this a dipole moment. Di meaning two, dipole moment. Moment is a physics math word. In this context, it really kind of means balance. It actually technically means torque, but I don't want to go into that with you. It is basically telling us that there's two ends of the molecule. So let me give you a kind of picture of all three of these, and then we're going to talk about what we'll end up doing with it. I started with HCl. if I was to draw a electron cloud, we would draw it something like this. Kind of like a snowman, but the idea is where more of the cloud is, that's where it's more negative. And this would be marked this way. Partially positive, partially negative. That little symbol there means partial. Partial positive, partial negative. If I had the chlorine to chlorine, we would draw our cloud that way. It's a symmetrical cloud. No dipole moment. If I was to take and have or no opposite ends, that water molecule, what we would picture is something that looks like this. All right? Most of the negative down here. And as a result, we'd say that this end of the molecule is partially positive, this end is partially negative. The sodium chloride would look like this. And we don't use this symbol partial. We say that this is positive and this end is negative and this end is positive. There's been a complete transfer taken place. So what you're going to do this evening for me is out of your book, and it is problems 22 through 28 on page 364. I'm just going to do it that way, and you can send it to me because I do need to see you. Oops.